Hello everyone. Today we'll learn about the Prim's algorithm. Prim's algorithm is used to give minimum spanning tree. There is one more algorithm that produces minimum spanning tree from a graph. It's called as Kruskal's algorithm. I have already made a video on that. You can click on the I button to watch that video. Coming back to the Prim's algorithm, it is a greedy algorithm. As in, at every node, we check what are the available edges and we choose the edge with the minimum possible weight. To get the edge with the minimum possible weight, we maintain a data structure known as Min Heap. We'll begin with understanding some of the basics of the graphs. In undirected graph, the edges do not point in any direction. But on the other hand, in directed graph, the edges point from one vertex to another. In connected graphs, there is always a path from one vertex to any other vertex. So in this case, if we have to travel to vertex number 2 from vertex number 0, you can either go with this path or you can go with this path. In weighted graph, every edge is assigned certain weight. A spanning tree is a subgraph of an undirected connected graph which includes all the vertices of the graphs with the minimum possible number of edges. So in this case, the original graph has 4 edges to connect 4 vertices, but we can connect these 4 vertices only using 3 edges. So that's why the spanning tree will look like this. For an undirected connected graph like this, there can be multiple spanning trees. These two are the examples of the spanning trees for this original graph. A minimum spanning tree is a spanning tree in which sum of the weights of the edges is as minimum as possible. For example, for this original graph, this will be a minimum spanning tree because sum of the weights of the edges is minimum in this case as compared to this spanning tree. A minimum spanning forest is a collection of minimum spanning trees. If you are given a non-connected graph like this, then every connected component of this graph will produce a minimum spanning tree. For example, this connected component will produce this minimum spanning tree, and this connected component will produce this minimum spanning tree. Collection of these two minimum spanning trees will be called as minimum spanning forest for this graph. To produce minimum spanning tree, we can start from any node. In this example, I'll start with node A. Node A has two edges, one going to node B with weight 1 and another going to node C with weight 4. I'll add these two edges to our minimum heap. Here, the first element is source node, which is node A. The second element is destination node, which is node B. And third element is the weight of the edge. Now, our min heap is not empty. So we'll remove the element from our min heap with the minimum weight. Node B is not yet visited. So we'll add an edge between node A and node B. Now we'll see what are the edges from node B to other nodes that are not yet visited. And we'll add them to our min heap. There's an edge going from node B to node E with weight 7. There's an edge going from node B to node D with weight 8. And there's an edge going from node B to node C with weight 3. Now the job of this element or edge is done. So we'll remove it. Now we'll remove the next element from our min heap. That is an edge from node B to node C with weight 3. Node C is not yet visited, so we'll add an edge between node B and node C. We'll see what are the edges from node C that are not yet visited, and we'll add them to our min heap. Now we'll remove the next element from our min heap, that is AC4. Since node C is already visited, we don't need to do anything. Now we'll remove the next element from our min heap, that is CD5. Node D is not yet visited, so we'll add an edge between node C and node D. Now we'll add all the edges from node D to the nodes that are not yet visited to our min heap. Now the job of this edge is done, so we'll remove it. Now we'll remove the next element from our min heap, that is CF6. Node F is not yet visited, so we'll add an edge between nodes C and node F. We'll add unvisited edges from node F to our min heap. We'll remove the next element from our min heap, that is FE2. Now node E is not yet visited, so we'll add an edge between node F and node E. Now we'll add all the edges from node E that are not yet visited to our min heap. There is an edge from node E to node D with weight 9, but that is already present in our min heap, so we won't add that. There's an edge between node E to node B with weight 7, but again, that is also present in our min heap, so we won't add that. This node F is already visited, so we'll only add an edge between node E to node G with weight 1 to our min heap. Now we'll remove the next element from our min heap, that is EG1. Node G is not yet visited, so we'll add an edge between node E to node G. Now we'll add all the edges from node G that are not yet visited to our min heap. So from node G, there is an edge to node E, but that's already visited, so we won't add that. There is an edge from node G to node D, but that is already present in our min heap, so we won't add that as well. There's an edge between node G and node F with weight 4. Again, that is also present in our min heap, so we won't add it. So the job of this particular element is done. Now we'll remove the next element from our min heap, that is FG4. Now node G is already visited, so we won't do anything here. Now we'll remove the next element from our min heap, that is BE7. Same, node E is already visited, so we won't do anything here. Now we'll remove the next element from our min heap, that is BD8. Again, the node D is already visited, so we won't be doing anything here. Now we'll remove the next element from our min heap, that is DE9. Now node E is also visited, so we don't have to do anything here. We'll remove the next element from our min heap, that is DG10. Now here node G is also visited, so we again don't need to do anything. Now our min heap is empty, and as you can see, our minimum spanning tree is created with 6 nodes. Now let's talk about the time and space complexity of the Prim's algorithm. Here we are using min heap, and at a time min heap can have maximum v elements, where v is the number of nodes or vertices in the graph. So the space complexity would be big O of v. We also know that if a minimum heap contains v elements, then the addition or removal operation on min heap would need big O of log v time. So the time complexity would be big O of v plus e into log v, because we are visiting all the nodes and edges exactly once. Now let's look at the Java program for the Prim's algorithm. Let's say there is this graph which is represented by this adjacency list. Node 0 has 4 edges. The edge between node 0 and node 1 has the weight of 3. The edge between node 0 and node 2 has the weight of 0, and so on. We pass this adjacency list to get minimum spanning tree method. We'll initialize this min heap using priority queue. Every element inside this priority queue is an edge, where the first element of the edge is the source node, second element of the edge is the destination node, and the third element of the edge is the weight of that particular edge. Then we'll initialize some variables here. We'll initialize this visited array to keep the track of all the nodes that are visited. And then we'll keep this array list to store our final minimum spanning tree. Here we are adding an empty array list for every node in the graph. Now we'll choose the 0 as a starting node. So we have to visit the node 0, and we'll add all the edges from node 0 to our min heap. Then, while min heap is not empty, we remove the element from our min heap, where the 0th element is the previous node, first element is the current node, and the second element is the weight. If the element is already visited, then we can skip that particular element. If not, we can mark that element as visited, and we can add an edge between the previous node and current node. After that, we iterate over all the edges from the current node, and if the neighbor of the current node is not visited, then we add it to the min heap. In the end, we convert our array list of MST to the array format which we need as an output. If you like this video, then please hit the like button, share it with your friends, and subscribe to our channel.